Hi, everybody. Thank you very much for coming out to the first theory seminar of the semester. I'm very excited to introduce Roie Levin, who did his PhD at Carnegie Mellon with Anupam Gupta. Afterwards, he was a Fulbright Fellow at Tel Aviv University, working with Niv Buchbinder. Most importantly, he's a Brown alum from 2015 and was my Models of Computation head TA like 10 years ago.
With Anna.
With Anna,
Yeah.
like 10 years ago. Which I guess is like his, yeah.
And now you're
peak of his career.
Yeah, peak of his
absolutely
career.
your professor before me, like yeah.
And
Usurped the order. Yeah.
And he's now a professor at Rutgers as of this semester.
Thanks, Ellis.
Notably, the theme of the class is the Korean.
Oh, that's right. Yeah. Okay, thank you for having me. It's very fun to be back. I'm going to tell you about some work that I did during my postdoc. This is joint with Cheyenne, Niv, and Thachapol. And the paper is called Chasing Positive Bodies. I'd like to tell you what the heck this is about. So here's the motivating problem that's going to kind of set the stage for what we want to do. We're opening satellites, okay? We have some set of satellites that we want to open, and we have people that we want to serve. Okay, so in this representation, satellites on the left, people on the right, there's an edge between satellite and a person if the satellite is near enough to give them Wi-Fi. And we want to open the smallest number of satellites such that everybody has Wi-Fi. Okay, but the problem is actually more interesting. So people don't stay put, right? They move around. So in our model, people are going to come and go. And as they come and go, as soon as someone enters the system, we want them to immediately be served Wi-Fi. Okay, so someone shows up, maybe we turn on a satellite, give them Wi-Fi. And then when someone leaves, we might have unnecessary satellites. We want to save on operating costs, so we want to turn off satellites that are not in use. Okay, and furthermore, as this is going on, there's also some like overhead to starting and stopping satellites. So we also want to minimize the kind of churn between time steps, the number of satellites we turn on and off per time step. Okay, so this game goes on. Okay, what is this really? What's the kind of clean problem? This is really some dynamic version of the set cover problem. So if you're familiar with set cover, on the left-hand side, the satellites we're going to think of as sets, okay? And there's an edge, and the people are the elements, and there's an edge between a set and an element if the set contains the element. We want to pick the smallest number of sets to cover all the elements, okay? The people come and go, i.e. the elements come and go, and we want, what do we want? We want two things. We want an approximate minimum solution at every point in time. Okay, that's like approximately the smallest possible set of satellites open to serve everybody. And we also, as I said, want to minimize the number of edits per time step. And this notion of number of edits is also known as recourse in the literature. Okay, these are our goals. The question that underlies this work is, what is the recourse approximation trade-off landscape like? So clearly at the two extremes, like if all I cared about was approximation, I wanted just the minimum solution, I could just pretend every time step was like a freeze frame of like a static set cover problem. I'd solve it offline, and I'd get kind of the best I could do per time step. But now the recourse could be huge. On the other extreme, if all I cared about was recourse, I could just buy all the satellites at time step 1. That's a very expensive solution, but the recourse is kind of 0 over time. We want to understand the trade-off between these things. Any questions? Great. So set cover was, an arbitrary choice of problem. You can ask this question for all kinds of combinatorial optimization problems. So generally, you want simultaneously to maintain competitive solutions as the input changes. And second, you want to minimize the number of edits over time. Okay, and so people have studied such questions for a variety of problems. I mentioned set cover. You can study matching as either vertices or edges come and go, and you want to maintain approximately max matching while minimizing edits. Load balancing, here like the x-axis is like machines and these intervals are jobs. So I want to assign jobs to machines to minimize the max load on any one machine. Okay, and maybe the jobs come and go, and I want to do this while minimizing the number of times I reassign jobs. And maybe also a minimum spanning tree I might study. So at this point, this is becoming kind of a more mature area. It was new maybe 10 years ago, but there's kind of quite a lot of work in these things, including some of my own. Yeah. But that's all well and good. But the work I showed you on the last slide is often based off of kind of one-off combinatorial tricks. And what I mean by that is like you have to kind of think hard and come up with something that's tailor-made to your particular problem. And it tends to not generalize super well. Like there's not really like big design principles that we've discovered so far for designing such like stable algorithms over time. And the question we wanted to understand is like, are there general design principles, or is there a general recipe for designing low recourse algorithms? And in particular, we wanted to know, is there some analog of the LP relax and round paradigm? Okay, so bread and butter of approximation algorithms is this notion of LP relax and round. Like you write a linear program describing your problem, you forget about the integrality constraints, get some bogus fractional solution, and then you work really hard to round the fractional solution to an integral solution. This is like a design recipe for much of approximation algorithms. Is there such thing that we can make use of in the dynamic setting where the goal is like stable, consistent algorithms? Any questions? Great. So let me describe to you now like a meta-fractional problem, and I'll try to convince you that this is an analog of like linear programming for this setting. Okay. So we're going to play this game. You start with a point. Let's say it's at the origin. And then at every point in time, I'm going to show you a polytope. Okay, so time 1, it's k1. And your goal is to take this point and move it into the polytope. At time 2, another one shows up. You move it like this. And the goal is to minimize. OK, so you want to maintain a point xt that's always in the current polytope kt. And I'm writing kt as like the x satisfying some linear inequalities, just in this general form. Your goal is to minimize the total distance traveled, okay, of this game, as you serve or chase, in quotes, these polytopes. And we'll measure distance generally kind of in the LP metric. All right. So this problem actually is very famous. It's known as the convex body chasing problem. It was introduced by Friedman and Lineal in '93. And the goal was to kind of abstract all of online algorithms into some like very general meta framework. Okay, why is this kind of a suitable meta problem to be studying? Let's talk again about the set cover problem. Okay, so recall your goal is to open the smallest number of satellites to serve all the people. In this problem, let's say there's n sets, S1 through Sn. Those are the satellites. And let's let ut denote the element set at time t. And we'll have a variable xit, which indicates whether or not my solution at time t is using the set si. Then I can describe the body kt as follows. Okay, if I define kt to be the set of xt such that for every element that's in this active set, okay, that's the people currently in the system, I've fractionally picked at least one set covering that element. I've opened at least one satellite, to satisfy that person. And the second constraint I have is that my solution, okay, the total cost of my solution is the total number of sets I picked, is at most beta times opt, where opt t is like the optimal offline solution at time t. Like for this like fixed element set ut, there's some optimal solution with cost opt t. And I have this constraint saying like I want to be at most a beta approximation. So basically what I'm saying is like if I let this be my sequence of polytopes, then chasing these kt is equivalent to kind of maintaining a fractional solution that's at most a beta approximation at every point in time. Okay, and then like very kind of vaguely, the distance is going to capture the notion of recourse. Does this make sense?
Are you
Yeah.
allowing yourself to compute opt t?
Great
or
question.
Are you going to just prove that if some oracle computed opt t for you, you're within the bound?
So actually, we can use like LP surrogates for opt t. So you can compute basically like, there's a polytime like surrogate for the true opt t that works for our settings. But actually, in this whole work, we don't really care about computation time. So as in, we don't make any explicit mention of computation time, even though everything we do is polytime. But if it helps, just imagine you can spend exponential time and actually calculate opt t. Yeah.
This is fractional, though.
This is fractional. That's right. Yeah, and that's why you can use like a fractional surrogate for opt. Other questions? Okay, so back to the body chasing problem. So this is now going to be our first goal, okay, is to kind of try to solve a fractional version of this low recourse question in like very general terms, this meta problem. Is anything known about this? Turns out yes, so it's, it's a somewhat old problem at this point. Great news, there is an order n competitive algorithm, where n is the ambient dimension of this space. Okay. This was joint work and so two groups, so Argue, Gupta, Gorganesh, and Tang, as well as Mark Selke in 2020. They actually won co-best paper at SOTA for this, and it was kind of a breakthrough. So basically the punchline of this work is that there's an algorithm, and when I say competitive here, I mean like the total distance traveled by this algorithm is at most order n times the optimal trajectory length if you had full information about these bodies before the game began. So this is kind of amazing and incredible.
Over what time, how many time steps?
Awesome, independent of the time steps.
Yeah,
And that's the
yeah.
point.
I see.
Exactly. So there's no like dependence on time here. And it's actually like quite spectacular if you think about it that that's even possible. Okay, very cool. Unfortunately, yeah. Oh, it's the ambient dimension here. So yeah, it's, I'll talk about it in a sec. Yeah.
The input size is already grows with t, but it's the algorithm is in it.
Yeah, so I mean, look, we're maintaining a point in Rn, let's say. I should write that in the slide, but we're maintaining a point in Rn over t time steps, let's say. Like there's capital T of these bodies over time, but the dimension is like a fixed thing that's not related to t. Ask your question again, sorry, I think I confused you.
I couldn't parse it. Why could it be independent?
How is that possible?
Yeah.
Oh, I mean, that's their best paper. Like it's, yeah.
It's a competitive
Oh,
ratio.
Yeah, because it's not the total.
Oh,
distance traveled, it's
sorry.
What's the best distance compared to like the optimal?
Yes,
Right.
sorry. So exactly.
So maybe that's.
Like like your algorithm has an input and an output. And for your input, doesn't your input already have a every input, it takes already time t? Or you
But
don't
it's
have
not
it?
time order.
Yeah.
This is
It's
the
a
competitive
ratio.
ratio.
Yeah.
on-
Should I repeat the question, by the way?
Yes, you-
Okay, so sorry. So the question was like, how is it that there is no dependence on time here when the input already kind of has time in it? And the point is like, this is measuring, here's exactly what it's measuring. My algorithm's computing some, path with some length, let's say L. And then if I had full information, if I knew these bodies ahead of time, then I could do it better. I could do it like L prime. This is saying L divided by L prime is at most order n. But there's no like, I'm not talking about like computation time. I'm not talking about the absolute lengths. It's like the ratio of these things. Yeah, does that make sense? Yeah, that's for the competitive word. Yeah, good question. Okay, so this is like amazing, but it's basically up to polynomial factors the best you can do. So actually there's a lower bound of square root n, and there's an open question here that's very interesting. It's probably hard, but it's interesting. And this lower bound holds even for L1. It's basically for all LP, but including L1.
Sorry.
Yeah.
Lower bound is in this 93 paper.
No. The lower bound, the L1 lower bound is in 2020 or 2019 paper, I think. It's actually neither of these papers. It's like a precursor. There was like a flurry of like excitement around this
Sure.
question. Yeah.
Before the upper bound.
Like right before, like a year before, yeah. Actually, the L2 lower bound was known in the 93 paper. Yeah. Good. And I mean, there's this question about the dimension. So basically, like, this is amazing that it's independent of time, but actually, like, dependence on dimension is really weak for most combinatorial optimization problems. So recall in the set cover example, there's n sets. The dimension is the number of sets. So I'm allowing myself a slack of like n per movement of opt, I'm allowed to like buy or sell all of the sets. That's like a very loose bound, and it's not particularly impressive for this particular application. Okay, so what we want to know is, can we exploit more structure about combinatorial optimization problems we care about? Can we do better than this n bound that's very general for interesting special cases? And there is very nice structure to all the problems that I talked about. So set cover matching, load balancing, and spanning tree. We can write, just as we did for set cover, a sequence of polytopes describing the fractional kind of version of each of these. And they're really nice. Good news. All these problems are so-called covering and packing problems. Okay, meaning that they are polytopes described by linear constraints with very special features, that the constraints are either of the form Cx is greater than 1 or Px is less than 1, where C and P all have positive coefficients. Okay, so no mixing allowed. And this is where the term positive body comes from. Okay, so now you know the title of the paper. This is really great, and even better news is actually we did know, I mean, it wasn't phrased in this language exactly, but when we didn't have the P part, there was only the C, then it follows from prior work that you can actually get a log n competitive algorithm, okay, which is exponentially better than the n I showed you on the last slide. Okay, so this is very exciting. Okay, and yeah, this is a result of Buchbinder and Noer from 05. It's the celebrated online primal dual method in online algorithms. Okay, bad news. Actually, no, you can't. There's a square root n lower bound, even for this positive body chasing problem, even in L1. So from now on, we're only going to talk about L1, but that's not going to help us. Okay, so this was a short talk. Yeah. We want to thank Mark Selke for pointing this out to us after we wrote the paper. And it's actually quite fortunate he told us after, because we probably would have stopped looking if we knew about this before. Okay. Good. Nevertheless, the answer is yes. Okay, so for this positive body chasing problem in L1, recall it looks like this. So you're shown the sequence of polytopes with C and P that are positive, and you have to chase these things. Here's the theorem that we prove. Okay, so for positive body chasing in L1, we have an algorithm with total movement at most order log n times the opt, where opt here is like the total movement if I had full information. Right, what gives? Okay, awesome. Okay, my star went to the next line, but this is an asterisk. And clearly I've like misled you, right? So we are going to cheat a little bit. There's an epsilon hidden here in the big O subscript. Basically what we're going to do is we're going to maintain a solution that's almost feasible. We're going to actually violate the packing constraints by an epsilon. And the point is that, like, why is this not just, you know, a different packing constraint? Like, we're comparing ourselves to opt that is truly satisfying the packing constraints. So that's our benchmark, is the trajectory length with full information if you truly satisfy things. But online, you get to violate things a little bit.
I like to call it a bait and switch.
It's exactly a bait and switch. Yeah, exactly. Good. So oftentimes, this is a bait and switch, and it's like kind of getting around. Yeah, it's kind of a cop-out. It's going to turn out not to matter for a lot of our applications. So soon I'll show you like rounding results. Turns out you can also round these things to get truly feasible integer solutions, like an actual set of satellites to pick. And there you're going to lose extra stuff on the rounding, and this epsilon is not going to hurt you.
I have a question about the lower bound. Does it apply to pure covering problems?
No.
So is it in virtue of just the packing constraints?
Yeah, I mean, the packing set is empty in the covering land, and
Right.
so you can, you know, you're not violating anything.
That's right.
Right.
So this seems to say that, so the old result applied to any cover problem, the old
Yeah.
log n.
That's right. And yeah, since its introduction, it's been used like in a lot of it's like a subroutine in a lot of online algorithms. It's really useful. Yeah, including like getting me through my PhD. Like, yeah, very useful.
That's an important application.
Absolutely. Okay. Any more questions? Okay. So as I said, this is an exponential improvement over general chasing. And I want to claim to you that this is a dynamic analog of an LP solver, at least for the special case of covering and packing programs. All right. So I want to mention something about the guarantee that we give. Traditionally, those papers I showed you on that slide with all the citations, they have guarantees for the most part that are so-called absolute recourse bounds. This is our term, but their bounds are of this form. So over T requests, their algorithm has recourse at most C times T, or recourse is like the number of times I add or remove things from the solution. Whereas our bound is a little different. It says over the entire request sequence, no matter how long, the algorithm has C times opt recourse, where opt is like the optimal recourse if I had full information. So in some sense, it's like an instance optimal bound. It's giving me like finer guarantees about the sequence. So just a few more words. So as I said, it's an instance optimal guarantee. So take this example of a set cover instance, and maybe this element v6 is like coming and going on and off. Like the T bound, the like absolute recourse bound, would allow me to buy and sell this S6 over and over and over again. But maybe kind of, if I'm trying to be stable, like I'm okay with, it's much better to just buy it once and leave it fixed. You see what I'm saying? Like you can solve this problem with much less recourse, and kind of the T bound is not predicting that you can do that. Whereas this is a much finer guarantee, or S5, whatever. Okay, the second thing is that R bounds are robust to batching. They don't really care about the notion of time. In particular, like our matching and spanning tree algorithms handle both edge and vertex updates. It doesn't really matter so long as like there is an optimal sequence like that chases the sequence of bodies. It doesn't matter like in what form the updates happen. And finally, like sometimes absolute recourse bounds are impossible, or non-trivial ones. So maybe the only, like there are instances on which, you know, every algorithm has some like very, you know, trivial absolute recourse. So in particular, like this KLS paper of 2023 showed that if you're trying to solve fully dynamic load balancing, that's this problem with assigning jobs to machines, and you want to maintain a sub-logarithmic approximation, any algorithm needs poly n times t recourse in general. And poly n times t is a trivial bound to achieve because you can just kind of reconfigure the solution entirely at every step. And in their intro, they say to circumvent the negative result, one needs to consider a different measurement for recourse in the fully dynamic model. And I'm trying to tell you that basically we have a candidate for such a measure.
No, I think they serve different purposes.
They do,
right?
they do.
I mean, if I'm gonna buy your algorithm, I might want to know, okay, how bad can this get?
That's true, absolutely. You're totally
How
right.
bad can this be compared to
Right.
the other guy's algorithm?
So we're kind of saying, how much are you leaving on the table? As opposed to like absolutely like benchmarking this thing. Yeah.
So I don't think I'm understanding two correctly.
Yeah.
So does two mean that I can just give you a completely different graph, times 2+1, and it's the same algorithm?
So let me say it and tell me if I'm not understanding you. So take like you're maintaining a matching. This is a different problem. If I want to measure the absolute number of updates as a function of t, it matters if t is counting the number of times I add an edge or the number of times I add a vertex. If I add a vertex, I could be adding n edges at every point in time. And so like it's not like the actual bound will change drastically depending on the form of the update. Whereas if you're just, you know, matching the optimum thing, it doesn't really matter. Like there is an optimum sequence that's kind of hugging the, sorry, there's an,
I think she's.
say your question again, sorry.
Suppose you change the graph completely.
Mhm.
Okay, that's gonna hurt his algorithm a lot. But of course, it's gonna hurt the.
The optimal
The optimum
as
as
well, and so it's.
Sorry.
Okay.
Yeah.
All
Yeah.
right, so good, so you can do that.
You can do that. It's
Exactly.
gonna hurt everybody.
You're gonna be competitive.
Exactly.
The point is just be competitive. not-
Exactly. So as long as you can describe your sequence of updates as these covering and packing polytopes, our algorithm should be fine. It'll be competitive with the optimal thing. Exactly. Other questions? Okay, great. So I mentioned rounding very briefly. So we also in our paper,
So you're not actually gonna tell us what the algorithm is?
I will. I'm just, yeah.
Do you already?
If you want, I don't know.
You're already
Yeah.
talking about applications.
Sorry. No, because I'm showing you where it goes. Okay. So we also show how to round these things. And actually the fractional part's more interesting. The rounding was a proof of concept. Like, I mean, not to minimize, but it's kind of the first thing you would think of for most of these applications if you're familiar with how one normally rounds these things. But basically, so in this table, it's a lot of information. Don't worry about parsing it too carefully. This is prior work. This is our paper. There's two kind of relevant columns. There's approximation and recourse, right? We want to understand the trade-off between these things. And as I said, like the previous work have, for an approximation value, have like an absolute recourse bound as a function of t. And the point is that we more or less match for the same approximation ratios, sometimes better, can get something that doesn't depend on t. That's kind of competitive with opt. And of course, by virtue of these results having like t in here, this means opt is at most t. So we automatically get the same bounds up to polylog factors. That's sort of the punchline. Okay, and this line isn't, oh, okay, sorry. So opt here in this thing is the minimum recourse of any algorithm with the same approximation. And this is in red because the load balancing results actually insert only, as I said, for the fully dynamic version, meaning when things can come and go, there's that impossibility paragraph that I showed you. Okay. Okay, Anna, we can talk about the fraction algorithm if you want. Okay, so that's it. So that was the intro. Any questions before I dive into how this works? Okay. Again, most important that we understand, given that we're here, like what the algorithm is, and then the proof is like, you know, if we get there, that's fine. If not, also fine. Okay, so step 0 of the algorithm is to realize that actually it suffices to give an algorithm that only chases half spaces. I said we're chasing polytopes, but it suffices to chase half spaces. So why is this? I claim that any algorithm that chases half spaces competitively will also chase polytopes. Or we can make it chase polytopes. So suppose we're given a polytope that we want to chase. What we're going to do is we're going to feed the half space algorithm the defining half spaces of the polytope L times in kind of arbitrary order, round robin order, and then send L to infinity. So what I mean is like we'll just kind of go through the sequence of constraints over and over again and show that to the half space chasing algorithm. So why is this a good idea? Well, opt is feasible to the half spaces, right? The opt that chases the polytopes is also going to satisfy the half spaces, and it's finite, right? It just goes B-lines to the where it was going to go. If the half space chasing algorithm somehow was staying delta far from the polytope, then as L goes to infinity, it needs to pay delta times L, which goes to infinity. And it's competitive, right? Like we said, we're assuming that this algorithm is competitive with a finite objective, and so this can't happen. So this is essentially arguing that the algorithm that's competitive for half spaces necessarily needs to converge to the polytope, and therefore it's competitive for the body problem.
I missed something. Where do you show that the cumulative movement is bounded?
For opt, because it can just go to a point inside the polytope.
No, for your algorithm relative to opt.
I see. So assume for the sake of contradiction that I have an algorithm that chases half spaces.
That is not.
That is kind of doesn't converge to the polytope. Then as this number of rounds L goes to infinity, it kind of needs to pay delta times L. It's going to violate one of these like half spaces by delta or something. Like I'm kind of fudging what the distance exactly means, but morally this is like the point.
The optimal algorithm already knows it's gonna be a polytope.
Yeah.
So it knows that ahead of time just sits in.
It goes right there.
It goes right there.
But the half space chasing one is going to do a series of moves.
That's right.
And the cumulative distance, how do you look at the cumulative distance? It has to move over all those iterations.
So I know that it's competitive. I assumed that it was competitive with the optimal movement. Yeah. So it has to be finite in particular because opt is finite.
Yeah.
Okay, so but if it stays delta far from the polytope, it can't be finite. And so that's the contradiction. So therefore, it will converge to the polytope.
Oh, delta is your, I see. Delta is the violation that
exactly. Yeah.
happens.
Exactly.
Okay, got it.
Exactly. Yeah, I'm fudging like what exactly delta means, but
okay.
Make sense? Any questions? Okay, so that was just okay. Good, that's done basically. So henceforth, we're going to assume that our bodies are half spaces, and they're either covering half spaces of this form or packing half spaces of this form. Okay, so the point is all the coefficients are always positive in these linear constraints, and the variables are always on one side of the inequality. Okay, what's the algorithm for half spaces? Without further ado, when a covering constraint arrives, we're going to solve the following convex program. xt minus 1 is my solution that I got from my last time step. So that's like a fixed constant value. That's not a variable in this program. And xt is going to be the minimum x, okay? The x that minimizes the KL divergence between x and xt minus 1, plus some delta thing, which we'll talk about in a moment, subject to the constraint that X satisfies the new covering constraint. Does that make sense? Alice's question?
You said something about memorylessness before. What's the sense of memorylessness then?
I'll say more about it in a moment. Did I say memoryless? I don't know. Maybe you saw Neve's
Maybe
talk.
I said it needs.
Yeah.
Something somebody's done.
This algorithm only cares about the last, given the last point in time, it doesn't care about the history.
Okay.
Yeah, it's just the current constraint and the last iterate. And okay, so if you forget what KL divergence is, it's some expression. I mean, it's an interesting expression, but it doesn't really matter for the purpose of this talk. And delta is going to be some small value that you can discover what the value should be when you do the proof, but the point is think of it as just some small value. And I can say kind of philosophically why it's necessary to have this delta. And now when a packing constraint arises, we do something very similar, but not the same. We solve this minimum KL divergence program, but without the deltas. Okay. Any questions? And so these YT and ZTs are like Lagrange multipliers.
I'm confused, but there were two types of constraints. What are these constraints?
Sorry, so recall like we're now assuming everything is a half space. So the game is like someone shows you a half space, you have to go there.
Yeah.
And we assume that they are either covering or packing, because like the constraints defining our polytopes are always covering packing by assumption.
What's the covering?
Good, so covering looks like this, positive coefficients and greater than something. Packing is positive coefficients less than something. And it's
Sign.
exactly, it's like monotone up versus monotone down. Like if I have a covering constraint and I increase my variables, I only stay more feasible. Packing is like if I make my solution smaller, I'm only staying more feasible. It corresponds intuitively to like a resource that I need more of versus like, you know, something I have to reduce. Yeah, covering packing. Okay, make sense? Okay, great. So actually, this might look a little esoteric depending on your tastes, but it has a very simple like solution. So you can look at the KKT conditions. These are conditions at optimality of convex programs. And they actually say something very simple about the nature of the updates. You can actually write a closed form update for the solution. These kind of convex programs are just useful conceptually. So actually, so in the packing setting, I multiply my xi by some multiplicative factor. And this multiplicative factor is less than 1. So basically, it's saying like, take every coordinate and kind of push it down until you satisfy the packing constraint. Whereas in the covering setting, I'm doing almost the same thing, but with an additive update as well. So it's like a combined additive multiplicative update. And this is where you really need the delta. Because if you didn't have delta, suppose xt minus 1 was the 0 solution, and I just multiplied, like if I didn't have the delta, the update would look something like this. Then I'd be multiplying 0 by something. I'll never satisfy a constraint saying I have to be at least something.
If you only have packing constraints,
Yes.
the lower bound it sounded like the lower bound applied.
No, I don't think so. I think you need both. So packing constraints, you can flip to be covering constraints just by doing 1 minus your.
Oh, okay.
Yeah.
I
I mean, you.
that doesn't. Then it's not a packing. It's not in a non-negative orphan or something. No, I guess that's okay.
I mean, you do need an upper bound on your max variable
Yeah.
size, maybe.
Okay.
Oftentimes you can do
But anyway,
this.
the
Yeah.
lower bound does not apply.
I don't think so.
When you just pack.
Yeah. Yeah.
So it's the mix that's interesting.
The mix is what makes it tricky. Yeah. Any other questions? Okay. So basically, it's almost a multiplicative weight update. It's almost like an. I mean, it's up to this delta thing. It's an algorithm that multiplicatively updates my coordinates until feasibility, which is at least the dynamics are simple to understand. Alice, question? No. Any other questions? So the point is, okay, let me say this one more time, because this is a lot of symbols. I have a constraint arrives, and it's like a packing constraint that I'm violating. I'm like above it. I'm too big. So this is saying like, okay, reduce your coordinates multiplicatively, like cool everything multiplicatively until you satisfy this constraint. And the same for covering, but with like a little bit of an additive push as well. like do a combined kind of multiplicative additive update until you go above a constraint. Okay. How the heck do we analyze this thing? That was the algorithm. And I only know simple tools. So the primal dual method is the answer. Okay, so what do I mean by this? You can actually write an LP describing the total movement of the optimal algorithm. Okay, so what do I mean by this? Let's, oh, Ellis, can I? So sorry. All right. Sorry, last minute we changed computers. Okay. So the point is I can write an LP that captures the movement of the optimal solution if I had full information. So I have the objective, okay, the variables that I'm going to solve for are like the x's over time. And I want to solve, the minimum, I want to minimize like the total L1 movement between successive time steps, okay, of my solutions. And at every point in time that it's in capital C, that's a set of times in which a covering constraint arrives. I want to satisfy the right covering constraint. And in times in which the packing constraint arrives, I want to satisfy the packing constraint. And this, okay, this doesn't look linear, but you can make it linear. You can make it a linear program. You need to add a variable L that measures how much a variable grew. We're actually only, it's cleaner if you only look at like upwards movement. But it's up to a factor of 2 the same. Like if a variable goes down, it must have also gone up. So if I don't care about constant factors, I can just measure the number of times a variable, like t, t minus 1 went up to xt. Okay, and then we're just measuring how much x grew over time. And now this is a linear program, and we love linear programs. So we're going to forget about the first thing. This is just this. Sorry, bear with. This is just a linear program. And I think I'm missing something. Yeah. Oh, you want me to move that? Okay. Good. So what do we do when we have linear programs? Phil taught me this. You take their duals. Okay. So this is the dual of the program. And now we're going to use like the primal dual method. So we have an algorithm that outputs some solution over time, and we're going to fit a dual solution. We're going to exhibit a dual solution that's related to the cost of our primal solution, and then show that this dual solution is feasible. And by weak duality, this will mean that our algorithm is necessarily not too much farther than opt. Okay, so I'll say more in a moment, but basically like, sorry.
It's quite readable.
It is?
Yeah, I don't mind.
Oh, I see. Okay, I thought they actually weren't showing up, but it's fine. I think this is the end of the nasty symbols. So I suggestively, okay, so the dual program, wait, no, but I think we're missing some, oh no. It's just easier.
It's fine in your computer.
Yeah, I think my font
Sorry.
package is different from yours. Yeah. So the dual program has 3 kinds of variables in it. You basically, like, this is a mechanical process. You take a linear program, write a dual. Like it's annoying, but you don't have to think. And then when you do this dual has 3 kinds of variables. There's y's and t's and r's. And I suggestively called them y's and z's, excuse me. Y's, z's, and r's in this program. I suggestively called them y's and z's, even though we already had y's and z's as our Lagrange multipliers from the convex program. And the reason is that we're going to fit a dual solution by just jamming these y's and z's into that linear program. So there's 2 things going on. There's like this convex program that we use to actually like compute the next iterate in our algorithm. And then there's this auxiliary linear program, which is just kind of a proxy for the optimal solution. And so what we're doing is taking the Lagrange multipliers, which are like dual variables of these convex programs, and then jamming them into the dual of this like offline proxy for opt. And then we also have to set r's, but it doesn't matter. You set r's in some way.
So when you
Question.
say jamming them in, you're just like literally using the Lagrange multipliers.
Literally, as is. Okay, so basically like the Lagrange multipliers you get from this program plus this R that you define separately, basically you can show that those are feasible to the dual. Feasible to, you know what the end of this thing is. Okay, so how does the proof go? This dual that I described to you, which is the combination of these Lagrange multipliers and this R that you define separately, are feasible to the dual. The proof is just once you have everything set up, you can just check. There's kind of nothing interesting about checking it. The interesting part is like knowing to even do this in the first place. And the second thing is that the cost of our algorithm, which is computed by this convex program, you need to bound in terms of the dual objective. And so what we can show is that the algorithm's movement, its total trajectory length, is 1 over epsilon roughly times the dual objective. Okay. So if you've kind of zoned out, do we see why this implies the theorem?
Yeah.
So this is the primal dual method basically. Like the dual is super optimal if it's feasible. Like every dual is super optimal if it's feasible. So if I can relate the algorithm's cost to a feasible dual, then I'm basically showing that that algorithm is within whatever fudge factor of the optimal solution. So the final bound that we get is, the algorithm is at most opt times 1 over epsilon times log n over epsilon. The 1 over epsilon comes from this inequality, and the log n over epsilon comes from the fact that you actually need to scale down the dual to make it feasible. Okay. Just trying to. So I think we'll skip the innards. I don't think they're
Can you just
particular.
give a
Yeah.
little intuition for lemma 2?
Yeah, sure. We can even write it. So okay, this part is supposed to. So the annoying part about this proof is that this z thing you're subtracting. So your goal is to show that opt is less than something minus something, and that's it'd be easier if you didn't have the minus part. So actually, if you only had covering constraints, you wouldn't have this minus part, and we knew how to do that basically prior to this work, and the new part is handling the fact that you're subtracting something. Okay. The lemma comes from two things. So using these two ingredients, basically, from the KKT conditions and the fact that KL divergence is a non-negative quantity, which is an important fact, there's two inequalities you can deduce. One is that the algorithm is like less than some factor times just the positive part. Okay, and this is kind of what the morally was known. And then you can also deduce this other thing, that 0 is less than some other factor times the positive part minus some other, sorry, this is the same factor, but some other factor times the negative part, z. And the theorem comes from just combining, like a linear combination of these things actually yields this inequality. You can kind of tune things correctly. Like if you try to make the multipliers of y and z the same, you'll get roughly that you need to multiply by 1 over epsilon. I don't know if that answers your question, Phil, but turns out to do this argument, it won't work. There's no solution to this thing, to this linear system, if you didn't have the epsilon resource augmentation. And that is good because we know that it's not possible without the resource augmentation. And this is kind of the step of the proof that really needs it. You won't be able to kind of infer this inequality from these if you don't have the extra epsilon. We call epsilon was how much you're violating packing constraints by. Okay. This part I will skip. So basically, just to show you that it fits on one slide, it's not too bad. It's algebra, but you can chain some inequalities and kind of bound the performance of the algorithm in terms of the y. And through this proof, you discover what you should set delta to. Delta is that additive factor. Okay, so this is like technical innards. I don't have time, and I think maybe it's less interesting that we actually do this, but it is relatively simple once you have the framework set up. You can kind of absorb it offline. Okay, so philosophy, we like that more than math, right? Okay, yeah.
Can you say one word about why KL divergence is the right thing?
Yeah, here's a philosophical answer. Is that okay? Like,
That's what I want.
okay, so suppose we start at the uniform distribution. Our first point, we have no information about what's about to hit us. So maybe, and let's say we're living on the simplex, okay? We start at the, because I don't want to ignore the additive part of the updates. So we start at every coordinate's like 1 over n, 1 over the dimension. That kind of makes sense to start at the uniform. I mean, nothing else would make sense. And then the first constraint that arrives is we need to satisfy the constraint, and the uniform distribution is not satisfying this constraint. What we're saying is minimize the KL divergence between the new iterate and the uniform distribution, subject to the new constraint. That's equivalent to maximizing entropy subject to the new constraint. And so KL divergence is kind of naturally hedging towards the future in a smart way, like in fact, it's like the right Bayesian way to do it if my prior was the iterate from the last time step. Yeah, so people who know machine learning maybe have a smarter perspective about this, but intuitively it kind of is very natural. And the other answer is that the algebra is just kind of very nice. Like, we hold on to for dear life, anything that we can work with. Yeah, it has a lot of exactly nice properties. Other questions? Okay, so comparison to the older work. So the online covering work of Buchbinder and Naor actually is exactly our algorithm, but with only the covering part. So only the delta updates, and ours has this like 2-part thing where we do something different from do something different for covering versus for packing programs. And I've kind of highlighted the difference between what you do. And the asymmetry, right, so our algorithm reduces to their algorithm for pure covering, and the guarantees are tight in that case. So basically, you can't improve on our algorithm because in this special case, the guarantees are already known to be tight. You can't do better than like log n competitive, even for this special covering case, and this is the right algorithm. And the asymmetry is kind of the new and interesting part, and it's crucial for the analysis. You can't do it if you put the deltas in here. And as I said, you need this epsilon here. Okay. Yeah. Suggestive connections, if it doesn't make sense, that's okay. Come and ask me. But basically, like, the weirdness of this asymmetry, I think, was a conceptual barrier to prior work. Okay, the other connection I want to draw is I want to compare our algorithm to the Steiner point algorithm, which is how those two groups that won best paper solved the general convex body chasing problem. So their algorithm is very beautiful. I encourage you to go read it. This one is 5 pages long, and it won best paper. It's like a really simple, really beautiful algorithm. So here's the algorithm. So my body at time t-1 was this one, and my body at time t is this one. I need to move to satisfy the new body. How the heck should I do it? What they do is they calculate something called the work function. And the work function is a function of this metric space. And W of x is the optimal cost of chasing all the bodies until now, and then going to x directly. We don't care about computation time, right? We can spend infinite amount of time, but it's just some conceptual function that we can calculate of the space. One more time, it's like the optimal cost of satisfying all the requests I've seen so far and then going to a point x.
The x is the point in the new body?
It's just some function on the entire metric space. So everywhere in the metric has this cost. Now they calculate the level sets of this work function. Using standard online algorithms tricks, you can assume you just know the value of the optimal trajectory, like the length of the optimal trajectory, not its actual like trajectory, but just its length. You can assume you know this. So they show that the set of points with work function less than 2 times opt is a convex body, and then they go to something called the Steiner point of this body. It's some like fancy notion of centroid. And this is amazing. Like, they prove that this happens to lie in the new body because it's like within this level set of the work function. Its distance is like, it's less than 2 opt. It's okay. It's very beautiful. Really cool. Our algorithm is like very, simple in comparison. When we get a new body, as I said, we just kind of go through and iterate the constraints and then kind of satisfy those half spaces one by one. So we see this one, then maybe this one, and then maybe this one until we're almost feasible. And this is where the word memoryless shows up in my talk. Like, it's very memoryless in that, okay, the work function is encoding like all the history of the requests I've seen so far. It's really history dependent. And here you only care about the last iterate and the current hyperplane that you're trying to satisfy.
Right, yeah. Maybe you'll get to this.
Yeah.
Obvious question, it seems like, is there a more, now let's talk about computation,
Yeah.
right? There might be a lot of facets to that polyhedron.
Right.
So presumably in certain structured situations, you can get there without doing it iteratively over all the facets.
Yeah, that's interesting. That's not something we thought about. The problems that we had all have nice, concise descriptions. Actually, I should just say we kind of ignored the question of computation time entirely.
Sure.
But
But
that's
in
a
the
very,
applications that you looked
Yeah.
at, the
absolutely.
number of facets is small.
That's right.
Is
We
that-
didn't do non-bipartite matching.
Yeah.
Like, yeah, absolutely. And I think that's an interesting question. I'll come to like future work and like natural. So basically like the biggest future work direction is like use this for application X. Yeah. So that's a really great and legitimate question. Okay. Any questions? Any other questions?
It sort of doesn't make sense to me why you would use memory to calculate the next step, the MT,
Yeah.
right? Like, do you have any explanation intuitively or?
For their algorithm?
Yeah.
That's a good question. Okay, so I've repeated maybe one question so far, but the question is like, why do you need a memory full algorithm? So it's not fresh in my mind. I think for the general case, it's necessary in some sense. I don't remember why, but so I mean, okay, so simple strategies don't work. Like the greedy algorithm doesn't work. If I just beeline to the shortest distance, point, I just project onto the new body, that's not a good idea. This like typical centroid algorithm, if I try to go to the centroid of the next body, that's also not a good algorithm. So I don't have a great answer to your question, but it's I do remember that there is a reason. Yeah. Other questions? Okay, we're almost out of time, but that's fine. We're almost done actually. What we actually show in the paper is stronger than what I presented to you so far. We showed the same bound, but instead of n, we get an f here inside this competitive ratio. And f is something even stronger than n. It's the maximum row sparsity of any covering constraint, which could be much less than n. I won't have time to talk about this too much. There's some interesting, okay, this is crucial for some applications. So when this f is constant and you want a bound that is constant instead of like a function of n, like it's sometimes, yeah, trivial to get the function of n, you really need this f. And there's interesting technical ingredients that go into this. In particular, you can't possibly show this with a dual that's computed online in like a monotonic, okay, this is a technical thing. I'll skip this. Point is, okay, I can say,
I
yeah.
have another technical direction.
Sure.
Maybe I should be going in, but I start thinking, okay, what about minor free? What about if there's that kind of structures on the matrices? Can you
do better?
Yeah. So stronger than sparsity.
Yeah, actually, I'll say even one of my open questions that I'll talk about is related to this. I think it's a really good question. Yeah. The question made sense. Like, can you exploit even more structure to do even better? I think that's very, very interesting. Okay, I'll skip this point. This is the most technical part of the paper, actually, is getting around from n to f. Turns out to be tricky. Okay. 2 seconds about rounding. So let me skip actually the first rounding algorithm and show you a different one. So, okay. Sample application. So we have this fractional solution. Now we want to round it to an integral solution. So let's go back to the set cover example. Recall the polytopes in that example were x such that for all the elements in the active set ut, pick at least one set to cover that element. And our solution at every point in time is in beta times the static opt solution to that linear program at time t. So now for the second part, the end part of the talk, we assume we just have this fractional x. We want to round it to an integral solution. So opt t here is the cost of best cover at time t. The theorem that we show for set cover is of the form, you can maintain a solution for any beta. That's a parameter that you get to tune. You get to pick beta. You can maintain a solution with approximation log n times beta times opt. And the recourse is sorry. Logs, oh, one more, almost there. Okay, and I'm not gonna be able to do this live, so it's something that's not showing up, and the next thing will show up. If you set beta to be a constant, then you get logs, like a log here. The beta here was a constant, so we swallowed it in the big O. And then whatever didn't show up here becomes log squared times opt recourse of O of 1. And what is this opt? So this quantity here, I'm sorry for the rendering issues, opt recourse of beta, I'm defining to be the best recourse of any algorithm required to maintain a beta approximation. So that's my benchmark, is like opt that's maintaining a beta approximation. I'm going to maintain a log n times beta approximation, so it's slightly worse than this benchmark. And its recourse is like compared to this best recourse algorithm times some loss. That's the form of the guarantee. So we'll skip the group. It's very simple, actually. It's like basically a dynamic version of the standard rounding algorithm for set cover. Let me actually show you a simpler theorem, which is a different thing you might want to prove. Here we go. Okay, good. So sometimes people parameterize set cover by f. It's the same f that I showed you a few slides ago, but it's the covering constraint sparsity, or the max number of sets any element is in. And for those of you who like to solve set cover, you'll know that you can get an f approximation for set cover offline. So here we're going to get basically like approximation that's f times beta, and our recourse will be f log f times this like best algorithm chasing a beta approximation. So very simple algorithm. It goes like this. We have a fractional solution in our heads. If it goes above 1 over f, if every coordinate, if it goes above 1 over f, we buy it. And if the coordinate then drops below 1 over 2f, remove it. So why is this a good idea? Well, the cost of the solution is at most order f times beta times opt, and it's feasible. And the reason is that the fractional solution costs at most opt. Every coordinate has at least one, sorry, every element has at least one set covering it that has value 1 over f, because there's at most, f sets covering it. So if all of them were below 1 over f, we wouldn't be feasible. So I'll buy at least someone to cover everybody. And second thing is that every time we sell a set, it went from 1 over f to 1 over 2f. So it must have dropped by 1 over 2f. So we can charge kind of the amount by which we buy or sell the sets to how much the fractional solution moved, which we know is bounded. Okay, that's the flavor of these types of rounding algorithms. That's it. I'll skip bipartite matching. Also not too complicated. So in conclusion, I hope I've convinced you we introduced a fundamental primitive into dynamic and online algorithms. Namely, we can solve mixed packing and covering LPs. And one more time, here's the theorem that we show. And we use this to give state-of-the-art algorithm for set cover matching, load balancing, and MST. And here's the open questions that I alluded to. So big thing that I want to know is, can you round this for other problems? We have some upcoming work with Neve on rounding for clustering type problems. So none of this talked about clustering objectives. Natural thing you might want to have stable algorithms for. And okay, you want to close gap. So there's this gap of log 3 halves 1 over epsilon in our dependence on the packing violation epsilon, which I think is just an artifact of the proof between our upper and lower bounds. And finally, this is related to Phil's question. Are there other important intractable families of convex body chasing? So convex body chasing, this Friedman and lineal like meta problem, the promise was to abstract all of online algorithms. And as I said, it's kind of too weak for many combinatorial optimization things you might want to do. We talked about packing and covering as like a special class that's both expressive and tractable, but are there other such classes? And so I'm fitting the like minor free question into this thing. Like, are there kind of nice families of this super general question that admit nice bounds? That's all I had to say. Thank you for listening.